IT Learning Centre Summer Talks, and I'm really happy to welcome back our visiting speaker from the world of AI and machine learning, Professor John Schock from the University of Cape Town's Maths Department. So great to have you with us online, notwithstanding possible question marks about Wi-Fi coverage. So we'll all be patient. We know how that feels. John also has work commitments in Montreal, but he does have sort of a history in Oxford, roots history. So his research interests have included neuroscience, string theory, and of course, suddenly topical machine learning. So yeah, today we're looking forward to hearing from you about the world of modern AI, perhaps a little bit of insight into this. John said that he's very happy for us to ask questions as we go along. We're quite a big group, which is why most of us are finding ourselves muted. However, if you've got questions or comments, do sort of jump in with them if they seem relevant. Or if you were to write something in the meetings chat, then between us, we'll do our best to notice those and to perhaps give John a chance to address those, but it might be a little bit later by the time that happens. So yeah, I hope that you'll make John very welcome, give him plenty to think about, and a polite audience. So thank you, folks, and thank you, John. Over to you.
A pleasure. Thank you very much. Very nice to be back after last week. Nice to see some new names here, and welcome back for anybody who was around last week. Let me just attempt to share my screen. Here we go. Please let me know if you can see this. Is this visible in presenter view?
We can see it, yes.
You can see it. Okay, that's great. Okay. Sorry, you can just see the main screen, is that right?
Yes, that's it. We just see your slides.
Okay, fantastic. Unfortunately, I can't see anything other than my slides at the moment, so please feel free to just jump in at any time if you have any questions. So last time I managed to talk fairly incessantly for an hour, not leaving a great deal of time at the end and for questions. So hopefully today is going to be a little bit shorter, which will leave some time for questions either about this, or indeed if you have sort of general questions about AI, if you were around last time, any follow-ons from that, or just in general at the moment, I'm very happy to answer. So I'm going to be talking today about an area of machine learning called reinforcement learning, which is really the area that a lot of my research is focused on. And I'll give you a slightly less historical view of this than I gave of AI the last time. But hopefully by the end, it's going to make sense what reinforcement learning is and what it's useful for. Let's see, okay. So I actually want to ask you a question to start with. I'm going to go off full screen so that I can potentially see answers in the chat. I'd like to ask why you are here. This sounds like a rather sort of pointed question, but maybe Pamela, if you can read any answers to that, that would be great. Actually, I'm not going to be able to see the chat at all. But yeah. Just a very sort of strange open question. Why are you here?
Okay, John, just waiting for some answers to appear.
Sure.
That's interesting.
In particular,
yeah, go ahead.
In particular, sort of why are you here listening to this talk at the moment?
Well, we're getting plain old curiosity, which is eye-catching, to help people at Oxford understand how to use AI to do their jobs better. I need to keep up with developments. AI has been in the news. I want to know more. I'd like to know more, a lot of that.
Fantastic.
To hear some pros and cons, something about where IT is going, how it's going to affect our industry. So a lot of the people on the talk today are IT professionals. So, for us, all of those kind of things, but also I think a lot of broad, a bit worried.
Okay, yeah, no, those are all extremely useful answers. So hopefully some of those sort of reasons for being here will be satisfied by the end. I can't promise to satisfy all of them, but the reason I'm asking this question, in fact, is precisely related to reinforcement learning. And so I hope the reason that you're all here is that you feel that there is some value to you being here. There's some value in the sense that either It's going to help you potentially to alter what you know about the world so that you can apply it in your work, or you're going to be able to have more interesting conversations with people as AI becomes more and more relevant to us, or as somebody said, simply for curiosity, and that's actually something that I may talk about a little bit later. But that word value is going to be really important in what we discuss throughout this talk, because the point is that there being value in something, you have weighed up potentially a choice of two different things that you could have done. You could have come to listen to this, or maybe you could have had a nap, or maybe you could have gone to another meeting. And for some reason, and I'm not going to speculate why, you felt that coming here was the most valuable thing that you could do with that time. Oh, was there a question there?
I don't think so. I think it was just somebody typing.
Okay, no worries. So you presumably feel that there is some value in being here, and indeed you have made a choice that there is more value in being here than in doing the other things that you could have done. And that may not mean that right now it is the most sort of inherently rewarding thing, but over time you feel that it may take you to a place which has some inherent reward in it. And indeed, this is in some sense how we interact with the world all the time. Consciously or unconsciously, we make choices given the possible options in front of us about what we're going to do, and we make choices based on the value that we think one particular action is going to have. And those words, so reward, value, action, policy, are really the cornerstones of reinforcement learning. Reinforcement learning is all about how to get an artificial agent, and we're going to use the word agent here to mean some sort of programmed system which is able to act in a world. How do you get it to learn how to perform some task there are a number of ways of doing this, and I'll talk about a few of them, but by getting it to figure out what is the best policy to perform in order to increase its expected return over time. That means essentially going to the states in the space that have more value than other states. We'll define all of that in a moment. So the basic plan for this talk, I want to talk about where reinforcement learning fits into, the whole broad landscape of AI. And I actually showed the slide last time, but I want to go through it again. I want to just give some examples of what reinforcement learning can do. And then in the second part, I'll talk a little bit more about the details of it, about something called a Markov decision process. And then we'll want to define these things like states and policies and actions, rewards, values, Q values, all of these things. And then to look a little bit at how do we actually get a system to learn in some environment. A number of references. The most famous textbook on this is by Sutton and Bartow. It's just called Reinforcement Learning. It's a wonderfully readable book. There is mathematics in it. There is a bit of programming in it, but overall it's a very, very nicely written book. Deep RL Bootcamp on YouTube is very nice, and a YouTube channel called 2 Minute Papers, where essentially they talk about recent developments in AI, is also well worth watching. So in order to understand reinforcement learning, it's important to understand where it fits into sort of the whole landscape of AI. And I showed this slide last time, but essentially what we have here, all of this that we're looking at here is artificial intelligence, broadly speaking. Artificial intelligence does include machine learning as a part of it, but it also includes things which are not machine learning. And the real difference between AI, which is machine learning, and that which is not, is that machine learning is about machines learning from data that you give it or data that the machine gets. Artificial intelligence, which is not machine learning, tends to be about hard-coded rules that have been put into a program in something like what's called an expert system, where, for instance, you could go and chat to an expert system and ask it questions about how to perform some particular task, and it would have some database of answers, some if-then statements, which essentially say, if somebody asks this, go this route. If they ask this, go this route, and give them that particular piece of information. So there are different parts of artificial intelligence which are not machine learning, but we're going to be interested in those which are machine learning this time. So last time we actually spoke quite a lot about supervised learning. And supervised learning might be, for instance, fitting some particular function to a set of data. So here we have a set of data, which is, let's say, the percentage of people outside on a given day and the temperature outside. And you go and sample from maybe questionnaires, and then you can fit this data with a nice curve. And the way you fit that is using supervised learning. Here we have another example of supervised learning. This is a famous sort of public science effort, which was thousands and thousands of images of galaxies which people wanted to classify. And first of all, they were doing this, getting people to do it, but then it was found that it was possible to do this using artificial intelligence, using supervised learning, and in particular using deep neural networks, which is something we spoke about last time, and applying them to this classification task. So in this classification task, you show a machine a particular image of a galaxy, and you wanted to say whether it's a barred spiral or an elliptical galaxy or an irregular galaxy, these sorts of things. And it's possible to get a machine to learn how to do that given enough data. Then there's unsupervised learning over here. And in unsupervised learning, you might have some data set like this. And to us, it's sort of obvious that there are three clusters here. There's a cluster over here, there's a cluster here, and there's a sort of more diffuse cluster here. And we can look at it and say that there are three clusters. But maybe in some very high dimensional data set, where it's not just 2 dimensions as it is here, but maybe many millions of dimensions, it's much harder for us to see it. But in an unsupervised learning task for a computer, it can actually spot these clusters in data if the patterns exist there. Then we've got this idea of the generative adversarial networks up here, which is, again, the application of deep learning or deep neural networks to unsupervised learning tasks. And these generative adversarial networks are an example of that. And in particular, this is something called celebGANs, where all of these people sort of look somewhat like celebrities, but in fact, these people don't exist. Okay. It's a data set which has been trained on images of celebrities. Okay. And then the third branch of machine learning that we can talk about here is reinforcement learning, and in particular, deep reinforcement learning. So reinforcement learning, which I'll often call RL here, came about from bringing together 2 seemingly rather disparate disciplines, one of which was psychology, about the idea that people and animals learn through trial and error. So you've got some task, you try it, maybe something goes right and you're going to do more of that, maybe something goes wrong and you're going to do less of that. And that's how we learn, that's how animals learn. So that came from psychology. And then the idea of secondary reinforcers. And secondary reinforcers are about the fact that there may be one thing which you're really trying to do. Let's say you're trying to get a meal, but it might be that there is something that you can do in order to get the meal. And I'll talk about that in detail in a moment. Actually, no, I'll talk about it now. So that's really the idea of something like Pavlov's dog, where Pavlov would ring the bell, and sometime after the bell, sometime soon after the bell, the dog would be given food. And the idea is that the dog had this secondary sort of state, the ringing of the bell, which it then associated with the thing which actually had value, actually was the reward, was the food. But as soon as it heard the secondary reinforcer, the bell there, it knew that the food was coming. And so the bell itself then became valuable. The ringing of a bell isn't inherently valuable, but if you associate it with something where there is a reward, in this case food, then it is valuable. Then on the other side, there's optimal control, and this is an area of engineering and computer science. And the idea of optimal control is you have some task or some dynamical system that you want to be able to control. It may be, keeping an airplane stable. It may be balancing something, something where there's some dynamics going on, and you need some feedback mechanism in order to learn how to control a particular system. It might be the vibrations of something in a piece of machinery. We'll see in a little bit a really clear example where a robot is balancing a pole. And within this field, there are things like value functions, which is to do with how good a particular state is. If you're trying to balance a pole, then the pole being sort of off to one side or falling over is not a very valuable state. But where it's being balanced vertically, it is a valuable state. And there were techniques from optimal control theory, things like dynamic programming, which were used in order to solve these tasks. But then when you bring these ideas together, you really get the modern ideas of reinforcement learning. Well, that together with something called a temporal difference method, which we'll talk about a little bit later. That's really modern reinforcement learning. Okay, so here's a few examples of what an RL agent can do. And in this example, we're seeing an old Atari game. This is called Breakout. And the idea here is that the little paddle at the bottom should be controlled by the computer system, and it should move it so that the ball hits into the bricks, breaks the bricks, and you get points for doing that. And this system is learning through trial and error. It's taking on the order of 120 hours, but it has learned by trying some things, finding the points that it loses lives, trying other things, finding that it gets points. After a while, it's able to learn to play up to an expert human level. Then with a little bit more gameplay, so sorry, not 120 hours, that was 120 minutes. Now with 4 hours of training, we actually see that it finds, essentially, it's not quite a bug in the system, but it finds a way to solve the problem in a much more efficient way than probably most humans would. And we'll see that it's creating a little hole in the top left, and the ball bounces around at the top, and it's able to solve the task even better than most expert humans would be able to. So the point is that nothing has been programmed into this agent, the thing which is controlling the paddle at the bottom, to say, if the state of the game is like this, you should do this. If it's like that, you should do that. It learned it through trial and error. And that's really the fundamental idea of reinforcement learning. So what did it do? Well, it used trial and error learning. It tried something, maybe the ball was coming down and it moved to the right, and so it lost a life. And so it knows that in that state, if the ball is coming down to a particular place, if it moves right, it shouldn't do that. So maybe it'll try and move to the left the next time. And in doing so, it will accrue more points and know that indeed that does seem to be the better action to perform in that particular scenario. Another example, this was Google's DeepMind AI, which we'll talk about in more detail. Essentially, this is the same sort of thing. This little animated agent with legs, this was a quadruped here. Through trial and error learning, I hope that you can hear me over the music here. We'll turn this down a little bit. Through trial and error learning, the agent was able to learn to move. This is one which is sort of even more humanoid. It may not run like most people run, but it started off not knowing how to run at all. The reward that it got was for getting from A to B, and we'll talk about reward in more detail as we go along. But essentially, the idea of reward is the programmer puts in the reward into the system. It says, the thing that I want this agent to learn to do is to move from A to B. And as it moves further along from A to B, I want to give it more points. And in this case, the reward is always going to be some number that it gets. And it's trying to optimize this number. It's trying to get as high a score as possible. And you can think about it purely as a score. It tries to do things such that its score increases over time. And the score in this case is defined by the programmer. It's defined by the creating the system. But the beautiful thing about this is that essentially that's all the programmer needs to do, is to define the reward, define the scoring system for it, and then having defined the particular learning algorithm that the agent will have, the agent just tries over and over and over again, sees when it gets more and more score, and does those things more into the future. Self-driving cars are another example of using reinforcement learning systems, but as I'll talk about a little bit later, one where one has to be very, very careful. You can't put a car onto the road and get it to learn purely through trial and error. That's going to go horribly, horribly wrong, and so one has to do it in controlled ways, in simulated ways, in ways which are only sort of additional ways of learning on top of other ways. Within manufacturing as well, it's extremely useful. And within manufacturing, the scoring system that one might want to introduce is something like to minimize waste, to speed up a process. So if you could have any waste products giving you a negative score and let the system learn how to manipulate the robots such that there is as little waste as possible while optimizing for time, again, you can use a reinforcement learning system for this. So this is a really classic example. It's called a swing up cart pole. I've sped this up a little bit. Essentially, what we have here is a computer which is controlling the little robot which moves along the track. And it can move it from left to right. And the aim here is for it to get the little robot arm to stand up by balancing it. This is just a balancing problem. Now, one could think of doing this by coding in all of the physics and saying that, you know, if the arm is falling to the left, then move further to the left to accelerate underneath it. But that's actually rather complicated and is dependent on all sorts of things like friction and air resistance and things which maybe the programmer might not know about. In this case, all you have to do is to say, try different things until you start to get some score, which means essentially to have the pole slightly vertical, and then do more and more of that. And what we see here is that after a very, very short amount of time, the computer is able to learn to perform this task basically perfectly well. And this was about 15 seconds here of experience that it needed in order to learn to do this task. And the beautiful thing about this now is that if we were to change the task just a little bit, maybe add some more friction, or as you saw there, sort of push on the robot arm from above, try to disturb it, it's able to come back from that and learn how to deal with a scenario like that much more easily than it would be if you had to program in all of the fundamental physics from scratch. So the question now is, how can we get an agent? And when I say an agent, I generally mean, again, a computer program, which is the thing which is trying to perform these actions. How do we get it to do this? Well, what is the agent actually attempting to do here? Well, we're going to use the word policy here. And a policy says, if I'm in a particular state, you know, that may be that the arm of the swing up cart pole is at a particular angle and I'm moving at a particular velocity. If I'm in that state, what's the thing that I should do? A policy is simply the action that I should perform given that I'm in a particular scenario right at the moment. And essentially, what you want is that the agent will learn the optimal scenario such that it can perform the task as well as possible for all possible states. Okay. The thing that we're trying to get it to do when we say optimally, to perform task optimally, is to maximize the future rewards that it can get. Now, in the case of cart pole, what we mean is by reward, the programmer might code in that if the arm is balanced within a certain angle of being vertical, then the agent will get some rewards. It will get some score. For every second maybe that it's relatively vertical, maybe it'll get a score of +1, and it gets a score of -1 whenever it's away from that angle. And so what's it going to do? It's going to try to find the policy that maximizes the amount of time that it's spent vertically, i.e. accruing points. Okay. Now, in order to do that, we can do it in a number of ways, but one is to define the value of being in a particular state. And in the case of the cart pole, any state which leads to being vertical is going to be a valuable state. Okay. So the policy here is the action the agent wants to do. And what it's trying to do is to move to states which have the highest value. That's essentially the idea of RL in a nutshell. So we need to define something here called a Markov decision process. And actually the details of why it's called a Markov decision process don't matter too much. But here's a really, really sort of simple example, an everyday example. Okay. We start off. Okay. So we have a set of states here. So the blue and the yellow are states, where the yellow ones are terminal states. So in this case, there's a starting state, which is in bed and need food. And there are various actions that you can take for being in given states. So for instance, if you're in bed and you need food, well, you could do nothing and you're going to remain in bed and needing food. You could get up. And if you get up, then you could be standing. And if you're standing, there are a number of things you could do. You could walk out the front door. You'll still be hungry. You could go to the kitchen, or you could go back to bed. Okay, so you can see the idea here. This is a sort of flow chart of the things that you can do in a given state. And what you want is to be satisfied by the end, having had breakfast, or you certainly don't want to be hungry as you walk out the front door. The point here is that if we were to define this as a task that a robot, let's say, had to do, if robots ate breakfast, was you would want to define a set of rewards here. And indeed, the set of rewards would be that you would give it +1 if it managed to eat breakfast and ended up in a satisfied state, or you give it -1 if it left the house or ended up browsing Twitter and was hungry. Okay, so these are the 2 bits of information that we give it, along with this whole process here, this so-called Markov decision process. Okay, so we can think then that any state which leads to the state of being satisfied, we can say is a valuable state. And if we are doing all the time the optimal thing, then even when you are in bed and you need food, you know that in the end you're going to be satisfied because you're going to do the right thing the whole way. And so we could say that that state in bed and need food has a value of +1 because it leads to a reward of +1 if you do all the right things. We can introduce something called discounting. And discounting is extremely important and essentially says the value of being in a given state is related to the future rewards that I can get. But if they're a long way into the future, several steps into the future, then I'm going to discount how important they are. So, for instance, we see that in bed and need food is several steps away from having eaten breakfast and being satisfied. And so although we know that we can get a reward of +1 by getting to that end state, we're going to say that because it's quite a long way off, we're going to end up with a discounted value for being in that state. The one where breakfast is made, but we haven't eaten breakfast yet, is very close to the state of being satisfied, but we've multiplied the reward by 0.9 to get us plus 0.9. Okay. In the kitchen,
Hello,
again,
can I just maybe bother you for a sec? Sorry, John.
Yes, please.
Hi, sure. A couple of us have noticed that your slides aren't changing. I think what's happened is that when you tried going full screen, it just froze on your keynote.
Oh, I'm sorry.
Now things have actually changed and we see the reward and the values and everything.
Oh, I'm sorry. Thank you very much for letting me know. So can you see that now?
Yes, we can. Yeah. I mean, if all else goes wrong, we can just stay in this mode without going full screen. And I think everybody can see this. Thank you.
Okay, great. So, sorry, just to reiterate that. So here, there's a +1 here for being satisfied. There's a -1 here. These are rewards for being satisfied and hungry. Here, there's value associated with being in these states, and there's a +1 here if we don't include discounting, because we know that we can go from here all the way to this state if we perform the right actions. And so we say that this state is valuable because it leads to the final reward of +1 if we do the right things. But then if we discount, we can say that the more steps we are away from getting this final actually important reward, the less valuable the state is. So although there is some value for being in the state because we see that it leads in the end to being satisfied, it's not quite as valuable as this state here where we are only one step away from being satisfied. We can also add in some uncertainty. So for instance, if you get up from here, well, it might be that you end up standing up, or it might be that you faint. And if you faint, well, then you end up hungry. So we can think about a system like this where we know exactly the state we're in. We can perform some action, but maybe performing the action sometimes gives one outcome, sometimes gives another outcome. Okay. So this is really the idea here of a Markov decision process, where what I haven't talked about in any detail here is the decision process itself. So you know the right thing to do in this example is that if you do want to get food, then if you're in bed and you need food, you should certainly get up. If you do nothing, that's the wrong thing to do. So your policy should be, given that you're in this state, this is your action, which will take you to this state. And then you should take this action, which will take you to this state. Okay, so a policy is the set of actions given the set of states that you can possibly be in. And there is clearly an optimal policy, which is the one that leads to your final goal of getting the +1. And there can be suboptimal policies where maybe you'll spend a bit more time in bed or stand up and then go back to bed, etc., etc. So there are not quite an infinite number of there are lots of different policies that we can think about here, but there is going to be, in this case, one optimal policy. Okay. So the reinforcement learning framework is this. We have some environments, and the environment in this case was you're at home, and these are the states that you can possibly be in, and these are the actions that you can take. But it could be much more general than that. We have an agent with a policy, and the policy actually says, what's the probability that I should perform a particular action, AT, when I'm in state, ST? I think about it, I perform the action, and when I perform the action, it changes the state of the system. And that might mean changing the state from me being in bed to me being out of bed. It might be in a game of chess, it's a move on the chessboard. In a car, it could be move left or move right. And that's going to change the state of the environment. And when we say the environment here, we really mean the whole system. The environment then, having changed its state, is now in state S t+1 and gives us a reward. So the environment is essentially coded up such that there's some reward associated with it. The reward and the new state gets fed back to our computer system, so it now knows, right, now I'm in state st+1. It then looks at its policy and says, given that I'm in state st+1, what is the thing that I should do? Takes action at+1, and the system goes on and on. Just doing this, if you've got some fixed policy, then you will change your state in the environment. The important thing about reinforcement learning is that it can change its policy. And the question of how to change the policy is all to do with whether the rewards that it's getting are more or less than maybe it expected to get in that particular state. Okay. This doesn't sound like a very creative sort of system. Something like cart pole, which is this thing with the pole on top of a cart, or even a self-driving car, it doesn't seem to be particularly creative. There was a beautiful example from just a few years ago from the DeepMind team. They programmed a computer system using reinforcement learning, and this was called AlphaGo, and it was playing this game, a very ancient East Asian game of Go, played particularly in China and Korea and Japan. And Go, in some senses, is even more complicated than chess. And the reason I say that is because there are many more possibilities of different states of the game than there are even in chess. And in chess, there are an enormous number of possible games. In Go, it's astronomically higher. The person that we're seeing here is Lee Sedol, who for many years was the world champion Go player and was seen as one of the greatest of all time. There's a beautiful documentary which you can find on YouTube. It's called the AlphaGo documentary. It's all about the way this computer program worked and the whole process of playing AlphaGo, this computer game, against Lee Sedol in a championship. Before this, people had said that this game was far too complicated for computers to play. Just too many possible moves, too many possible states. It was impossible to get it to play it. Even though we had managed to get a computer quite some time back now to play chess and was able to beat Garry Kasparov when he played against Deep Blue, that was a different system because that was a lot more like handcrafted sets of rules. This used reinforcement learning. And essentially the way that it worked was it was set off with learning from human games, and then it played itself again and again and again, many millions of times, essentially learning what's the type of move that, given that it's in a particular state of the board, that it should make in order to increase its chances of winning. And it played against itself millions and millions of times until it attuned itself to really have an amazing grasp of this game. So the world's Go players didn't think it was going to be possible that it could beat Lee Sedol. He was so far ahead of everybody else. But when they came up against each other in a 5-game match, not only did it beat Lee Sedol, but it really kind of smashed him. It got 4 out of 1, and the one time it seemed that there was some sort of bug in the system. The really interesting thing came in one of the games, I think it was game 2 or 3, and it's called Move 37. And in Move 37, the computer made a move, and the commentators around the world thought that the computer had just made a mistake. It did something that just looked completely ridiculous in the given position on the board. If you look at the recordings, you'll see the commentators from around the world sort of looking with sort of incredulity at the ridiculousness of this move. Clearly the computer's gone wrong. Lee Sedol saw the move and went and sort of walked around for a while. He left the room, went for a smoke, and came back. And Lee Sedol knew that something was different here. He knew that something was odd, but what he realized was that the computer had played a move that no human would ever play, but that it had seen a different way of playing the game than any human had ever seen. What it had done is opened up an entirely new avenue of ways to play this game. This game, which has been played for many, many hundreds of years, in fact, thousands of years, this game has been played. And nobody had ever realized that the game could be played this way. And for me and for many people, this is really the definition of creativity. It's the creation of new concepts, new ideas, new patterns which have value. And this was clearly something which was novel and had value because it changed the world of Go. It may not be the same as creating art to many people, but to those who were in the Go community, this was something really profound and really beautiful, that it had created a new way to look at this game that nobody had ever thought about before. And this was purely through using reinforcement learning, through trial and error learning. So the idea here is that generally trying to teach rules is really difficult, because if you're trying to teach something like Go or chess, well, you have to come up with a rule for each different type of position on the board, and that's really difficult. But if a computer is able to learn for itself, then you have to do very little work. Of course, you need a decent amount of computer power, because in the case of AlphaGo learning to play, it had to play itself for many millions of games. But given the computer power, you can just press, Go and let it run. And over time, it will get better and better and better, and eventually far better than any human player would ever be. Okay. In fact, all of these things that we've looked at so far have this in common, that it's really about some sort of evaluative learning. That is, that it performs, the agent performs some move, it does some action, and there is some evaluation as to how good it is. Yes, you win the game. No, the angle of the arm was off by a certain amount. You never tell it what the thing that it should have done. So you never say to the cart pole, you should have moved a bit more to the left or to the right. All you say is, yes, that was good, or no, that was bad. And it turns out that that's enough precisely to define a reinforcement learning system. So just to formalize this a little bit more, and I'm not going to go into too many details here, a lot of the mathematics behind this came from Richard Bellman in the 1950s, the so-called Bellman update equation. He was a pioneer in the work of optimal control theory and dynamic programming, which is this area of sort of mathematics and engineering, which had been used in control problems. But when he introduced the idea of the Markov decision processes and brought these things together, that really gave us the beginnings of reinforcement learning. So we've actually seen this already, and I'm not going to go into this in too much more detail, but essentially the Markov decision process is this set of states, S0, S1, ST1, ST2, these are the terminal states, and that's the same thing as being in bed, finding yourself in the kitchen, being in the state of having eaten, and there may be some transition probability, the probability that if I take action A1 in state S0, I will end up in state ST1. And there's some set of rewards here, there's some set of actions and some set of states. And what we want to find is the policy, and it's called the probability of taking a given action given that you're in a given state. Again, I don't want to go into the details of it, but what's our aim? So I've said that you might want to win the game or whatever it is, but really what we're trying to do here, is to increase the expected future rewards. Okay, and in this case, there may be rewards not just for ending up in the terminal states, but maybe you'll get a reward of -3 if you take action A1 and you end up back in the initial state, which may be a bit like, you get up and you fall over and you end up back in bed. So there may be many different types of reward within the system. It may not just be for winning the game. It may be, for instance, for breaking a block in one of the Atari games. So the question here is, does the world seem like a Markov decision process? Well, this all seems very discrete. we start up in one state, we take an action, we end up in another state. And so this seems like a sort of discrete system where, of course, we're moving in fairly continuous ways, and our state is moving in a continuous way from some state S0 to some, infinitesimally different state. And so in some states, it doesn't seem that the world is really like this. But in fact, the world of continuous Markov decision processes is well understood. The other thing about an MDP, or a Markov decision process, is that you need to know everything in the system. Okay, so in this case, you know exactly the state of the system. But of course, most of the time in some given system, you don't actually know what's around the corner. You can maybe make some guess about it. But the point is that very often the world is only partially observable. I don't know what's happening right outside at the moment, but I can still make choices based on what is likely to be happening outside. I've got some observation at the moment that I'm not hearing any rain, so I should probably take the action that if I go downstairs, I don't need to take an umbrella, but I need to think about the probability that maybe it will rain later. So I don't have perfect knowledge. The other thing is that the past states are often very important. And one of the things about a Markov decision process is that the state that I'm in now defines everything. It doesn't matter how I got here. The state I'm in now is all that's important, but you can include ideas of memory into a given state in order to overcome that. Details don't matter too much. Okay. So what are we trying to do? Don't worry too much about the bit up here, but essentially this thing here, G of tau, we say, where tau specifies the path through our Markov decision process, essentially the set of states that we move through. This thing here is the total reward that we pick up over time. Would be the reward that we get at time 0, plus the reward that we get at time 1, all the way up to the reward that we get at the very end, which might be at some future horizon. And we write this in this particular form. The details of this don't matter too much, but what we're trying to do is to optimize the total reward that we can get in the system. And it may be that we want to include a discount factor. And so the way we do that is we just put in some number here between 0 and 1. And all this does is it makes the rewards far into the future be less and less important. Okay, so what that forces you to do is that if there's a reward in the future, you will want to get there as quickly as you possibly can. The idea here of psychic secretion, which was the translation of the idea from Pavlov's dog of the salivation that the dog had when it heard the bell, it's this relationship between rewards, where the food is the reward, and the thing that has value, which is the bell, because it leads to the reward, which is the food. And so we end up in states which don't have any reward associated with them, but have value associated with them, precisely because you can then get to states where there is reward associated with them after performing some set of actions. I haven't really talked about how you actually get a system to learn in this sort of environment. Generally, what you do is you start off by randomly assigning values for each of the states. Okay. So as an example, if I wanted to learn how to move in this system here, so let's say I don't actually know what to do. Okay, I'm in bed and I need food. I have a number of options of things I can do. I could do nothing, I could get up, etc., etc. I need to explore this environment. I give value, a random value to all of the states in the system, but there are these explicit rewards at the end. I take some actions, and what I'm going to do is I'm going to explore this environment until I get some interesting feedback about there being reward here. Okay, and it might be that I do this in some really complicated order. Maybe I start doing nothing and then I get up and then I go back to bed and then I get up and I take some very convoluted order. But by the time I get back to the fact that I'm finally satisfied in the end, I can feed this information back through the path and update the values such that I now know that because if I perform a particular set of actions, I can get to the state of being satisfied. I update the value here, which started off being some random value, with the new information. And that essentially is one of the cornerstones of how reinforcement learning works, is essentially I step from one state into the next state. I ask, how valuable is this next state? If it's more valuable than I thought it would be, either because it then leads to further valuable states in the future, or because there's some explicit reward associated with it, I then pass the information back to me in the previous state and say, hey, actually, what you thought in the previous state wasn't very valuable. Actually, it was, because I've just found out some information about how good this state is, because it can lead to a state with future reward. So there are lots of different ways of doing this. We can do it by iterating over the values. We can do it by subtly changing the policies. And really, there's this interesting interplay between the fact that the policy defines the value of being in a given state. A state is only valuable if the policy eventually takes you to the correct state. And the value itself informs the policy, because what we want to do is to always move to the states with the highest value. You can do this in the single agent case, where there's just one agent in the environment, but you can do this also in the multi-agent case, where you have multiple agents, and those might be, for instance, self-driving cars, where there are lots of agents, lots of individual cars moving, and they have to interact with each other in a way where, you know, they're clearly not crashing into each other, but they all want some sort of optimal outcome. They want to, you know, reach their destination fastest. But if they're all trying to reach their destination as fast as possible, not thinking about each other, then you're going to end up with traffic jam. You're going to end up with, you know, all sorts of terrible outcomes. So they need to coordinate. So within the world of multi-agent reinforcement learning, there's a question of coordination. How do you get agents to learn and coordinate together to get the optimal outcome? Offline reinforcement learning is also very important, precisely because something like in a self-driving car, you don't want to put a self-driving car on the road, as I said, and just let it, you know, experiment, explore for itself. What you really want to do is to take some offline data, for instance, recordings of people driving, and see if the self-driving car can learn by observing the behavior of other people. Clearly, it doesn't want to do exactly what people do, because if it did exactly what people do, there'd be not that much point of having self-driving cars. We want self-driving cars to do better than people can do. And so you wanted to learn from that and notice the optimal behaviors within that, and then take that to the real road and explore within some set of parameters. The state of the art, I just wanted to give a couple of quick examples here, and then I'm wrapping up, I promise. So NeurIPS, which is one of the main three artificial intelligence machine learning conferences that happens every year. In 2022, I had 164 papers, more than 164 papers on reinforcement learning in it. It's a really, really important area of machine learning, but isn't one that a lot of people, I think, know about, which is one of the reasons I wanted to talk about this. One of the papers that I saw, which I really liked from last year's NeurIPS, was this towards human level bimanual dexterous manipulation with reinforcement learning. And essentially that's saying, how can you get a machine to control robotic hands in a way which is as dexterous as a human? And people are now getting there. DeepMind, Google DeepMind, which created AlphaGo, has also created AlphaFold, which works in a different way, but it's still a reinforcement learning based system, and it's able to take the molecules in some protein and figure out exactly, or take the atomic structure of some protein and figure out exactly what the three-dimensional structure of it is. And this is a problem that has been extremely difficult for many decades, and we seem to be getting there. They've come an enormously long way in figuring out the three-dimensional structure to proteins, which is really what's needed in order to figure out their function and how you can create novel drugs to cure diseases and many other different avenues. So I think I'm going to stop there. We've got a few minutes. I don't want to run on as long as I did last time, so I'm going to stop there for now. If there are any questions about reinforcement learning or about anything from last time or AI in general, I'm very happy to answer them. I'm going to stop sharing for now. Yeah, thank you very much. Are there any questions?
John, thank you very much. Lots of things. I'm going to kind of jump in with something a bit more of an arm-wavy question. I wondered if you had thoughts on the increasing role of AI in higher education as a university lecturer yourself. Benefits, challenges, end of the world. What do you think?
Yeah. So, we find ourselves in a truly fascinating time at the moment in terms of particularly generative AI, things like ChatGPT, which I spoke about briefly last time. But I think that there's lots of uncertainty. There's lots of uncertainty, both with where we are now in terms of things like ChatGPT and where it might be in a year or two. So I can give you my perspective as a mathematics lecturer on the utility of things like ChatGPT. I think that I've seen some people, trying to ban students from using things like ChatGPT, and I think it's really, really difficult to do that. I think it's very difficult to try to, stop a tool from being used once it's out. So my quest is to try to get students to be able to use it in productive ways. And so I've asked them to find the ways that they can best use it as a sort of tutor. And so one thing that you can do is to use it as a sort of Socratic teacher. So you might say, I would like to learn about a mathematics topic, let's say proof by induction. Please teach me proof by induction in the style of a Socratic teacher. And so I'm asking my students now to go and experiment with this and then come back to me and tell me the useful ways that they do it. In the tutorials, I find students from time to time using it to help them with tutorial questions. And, I think with all of these tools, it can be used in a positive or a negative way. And when I see them using it, I go over and I speak to them and I try to find out the ways that they're using it to improve their learning, not just to answer the question, but to actually improve their learning. And so far, what I'm finding is that they're actually generally using it in fairly positive ways. I think that, in any subject where, for instance, you're getting students to go away and write essays, again, it's difficult. That there are clearly useful ways it can be used. I think that it can be used to generate ideas. And if you can look at them with a critical eye, that can be extremely valuable. As it gets better and better, and in fact already it's very difficult to tell, whether a student has just put in a prompt into ChatGPT, or whether they've used it in some helpful way, or they haven't used it at all. And so I'm quite glad that I'm not in a subject area where I'm getting students to write essays or the like. I think for more technical areas, because we tend to be exam based, it makes things a little bit easier for us. But I think that we're going to have to sort of change our ways of evaluating. But in the same way that, when we got Wikipedia, we were sort of warning people about the dangers of using Wikipedia. I think that we now know that it's a useful tool with caveats. So, it's something that can be used to guide you along the way. And I think that that's something that we should be using it for. It should be guiding us, or we can use it to guide us in finding answers, finding solutions. It shouldn't be the thing that gives us the answer, but it can guide us in that direction. Okay. I see that there are some other questions here. Do you think AI would be able to help in any way with climate change? Yeah, so absolutely. So in fact, one of the projects that I'm working on with an institute in Montreal is about climate change and about using machine learning to find materials which may be good for essentially absorbing carbon dioxide from the atmosphere. There are many different ways that AI can be used in terms of the modeling of the climate, in terms of technology, of producing less CO2, of carbon capture. So there are many different aspects of climate change that I think that it can be used for. I think at the moment it's really a question of timing. How quickly will we be able to use AI to create these technologies versus the quantity of CO2 that we're pumping out at the moment, and that's accelerating in many places. So I think that yes, it's extremely valuable. There was actually a white paper that was put out about 3 years ago, 100 or so pages, precisely about different ways that machine learning and AI can be used to tackle climate change. Yep, great question. Kevin there has a really important question. Well, all of these are important questions, but how can humans make sure that we stay employed in this sort of time of great acceleration? And part of the issue here is that we don't know what the future is going to look like. Things have changed so dramatically in the last year that it's difficult to know what it is that we're preparing for. And I think that in terms of educating, we need to be educating people who are flexible in their thinking, who are good problem solvers, who are creative. These are things that at the moment, AI systems, they may have aspects of creativity, but we have experience of the world in a way that at the moment AI systems don't. And I think that being able to educate people who are creative and flexible and who can see the things in the world around us that they think need changing, they can then utilize AI to make that change. So, as an example, I thought of an idea of an app a little while ago, which I think could be rather valuable, could be very useful. And I can now go to ChatGPT and I can say, please, can you show me how to code up this particular app? So in some senses, we can think back to the time that people were having to program using machine code and assembly language. And there was a massive barrier there in between an idea and how you actually code it up. You needed to know a massive amount about the way a computer worked in order to do that. Then we got onto having programs like, C++, where, you needed to know a lot less about the workings of the computer, but you still need to know about, the way memory is passed and pointers and all of these sorts of things. And now we're getting to a stage where you need to know very, very little about that. You can just ask a computer to, code up a simple program that does something. And at the moment, it's not perfect, but it's getting a lot better. And so I think that being prepared by learning how to use these tools, and by that I just mean experimenting with what you can do with the likes of ChatGPT, I think is really valuable. So for instance, ask it to write a program to do something, and then go to Google Colab, which is a free Google service where you can run code online, copy and paste it in, and just press go and see if it does the thing that you've asked it to do. Maybe it does, maybe it doesn't. If it doesn't, copy the error message, take it to ChatGPT, ask it what the problem is, and it'll try to refine the code. So there are lots of ways that we can explore the capabilities of this. Which of the applications of AI are you most excited by? What are the company's applications to watch in the next 12 months? Well, that's an excellent question. So at the moment, I wouldn't say it's quite the applications, but things like ChatGPT, I'm really interested in the synthesis of knowledge. So the incredible thing about these systems is that they know far more about all sorts of different areas than any human has. And what I'm interested in seeing is how this system can bring them together. So for instance, I can say, has anybody ever thought about using this mathematical technique to solve this physics problem? And maybe they haven't, but maybe I can ask ChatGPT to put those together. In terms of companies to watch in the next 12 months, I mean, other than the obvious, it's going to be interesting to see this sort of this race between OpenAI and Google DeepMind. I don't have any specific ones that I'm looking at the moment. So I see we've got oh gosh, there's a fair number of questions here. So there's a particular one here about about reinforcement learning. May I ask if there's a way to specify how long it takes for the AI to hit a particular reward? For example, we ask the computer to arrive at a target after 50,000 iterations and measure the amount of changes each iteration must make in order to do that. No, it's a great question. So generally, you won't specify how long it takes to get there. You'll put in some sort of discount. Generally, you'll want it to get there as fast as possible, but you could put in some sort of timing such that the reward grows in such a way that, if it gets there in 50,000 steps, it gets the highest reward, but if it gets there outside of that time, it gets less rewards. In terms of measuring the amount of change, it's rather difficult to do that depending on the type of system that it is. Certainly, you can look at the number of steps that it's taken along the way, but that's fairly dependent on the particular task. Recognize truth and what is false input based on learning, so in the end, it has no bias. So John, the question there is, that's a really difficult one, because in order to do that, you need a data set which itself doesn't have bias. You need a training set to train the agent to know, what is true and what is false. But to do that, you need to have a data set where you know it is true. And to have a data set which is large enough where there are no inherent biases in it, that's really difficult because humans are themselves inherently biased. And is one of the major problems with that we've seen in using AI in things like policing and the justice system, that, you know, you might think that an AI system is not biased, but it's trained on data, historical data, and that historical data generally does have bias. So trying to get rid of that tends to be very difficult. Can we use RL instead of neural networks for the same purpose? So in fact, in general, neural networks are used as sort of as a part of the brain of an RL system. So RL can be used to solve sort of supervised learning tasks where you might normally just use a pure neural network, so that can be done. But generally, neural networks are used in reinforcement learning systems to encode the value and the policy. I'm not worried about the future of AI, provided that there continues to be ethical, empathetic control of defining what's a good outcome. I 100% agree with that, Joseph. Yeah. There's an organization called Anthropic, which is actually looking at essentially at the alignment problem, which is, how do we think of ethics within, the development of all of these systems? It's an extremely important question. Yeah. And I think the answer is that it's not being thought about enough. It is being thought about more and more, but I think it's really vital that research accelerates. I think I should probably stop here as we're a little past 3 o'clock. Does that sound reasonable, Pamela?
Wonderful, John. What a tour de force. Thank you so much. Thank you for your, the things that you've taken us through. I think many of us have moved forward a long way in our understanding of these things. And thank you for gamely tackling the slightly random collection of questions at the end. Great pleasure to have you with us. I hope that other people have found it useful and interesting. I know some of the folk who came on last week's event kind of carried on the conversation, and at least one of them tells me that he's halfway through writing a blog on the conversation that arose from the talk. Yes. So let's see where the discussion gets us. But John, thank you very much indeed, and we'll hope to see you around in the IT Learning Centre again sometime.
A pleasure. Thank you very much. Thanks everyone. Bye-bye.